Hello. Today we're going to start chapter 10, which is all about conic sections. This is one of my favorite chapters to teach because of all the real life applications that you're going to see as we go throughout this chapter. Our goals for today are that you can find the key features of a parabola, you can write the equation of a parabola, and that you can graph a parabola. Let's start with a definition. A conic section, otherwise known as a conic, is the intersection of a plane and a double matched cone, which is just two cones standing end on end, as you can see. The four conic sections are circles, ellipses, parabolas, and hyperbolas. We're going to focus on the parabolas today. You'll see circles, ellipses, and hyperbolas as we continue throughout this chapter. Some more definitions for you today. A locus is the set of all points that satisfy given conditions. This is going to allow us to define parabolas and in fact all of the conic sections in a different way than you may have seen in the past. A parabola is the locus of points which are equidistant from a point called the focus and a line called the directrix. So every point on the parabola is the same distance from the focus as it is to the directrix. This little line connecting the point on the parabola to the focus would be the same length as that point to the directrix when that line is drawn perpendicular to the directrix. In Algebra 2 and Algebra 1, you may have only worked with parabolas that have a vertical orientation pointing up or down. And in Precalculus, we will also look at parabolas with horizontal orientations, ones that open left or right. One of the properties of parabola that make them very interesting is what happens when you place an object at the focus of the parabola and then reflect it off the side of the parabola. And for those of you physics people, you should know this property that the angle of incidence is equal to the angle of reflection. So when I reflect something off the side, and this is true if I reflect it off of a line or off of a curved object, this angle right here should be the same as the angle when it bounces off the other side. Okay? So let's look at what happens when we reflect off not just this one point, but if we were to reflect off of multiple points on the parabola. What do you notice about all of those lines of reflection? Hopefully you're seeing that every single one of those rays is parallel to the axis of symmetry. In fact, they're all parallel to each other. This is what makes parabolas so useful. This is why they get used for satellite dishes. Okay? If you have information coming from outer space, that information will reflect off the parabolic curve and reflect to the focus where the receiver is located. And then you attach a little coax cable to that receiver and hey, you've got television signals inside your home. Pardon me. Parabolas are also used in solar furnaces. This one is the world's largest, located in southern France, and is used to study materials at very high temperatures. These adjustable mirrors that you can see here, they can be adjusted depending on the time of day or the angle of the sun, depending on the time of year. Okay? So those sun rays are coming down, they reflect off the mirror, they come in here, then they reflect off this parabolic mirror, and all those rays of light will now be directed exactly at this focus, which creates a huge amount of solar energy. I believe, if I remember the research that I did correctly, that it actually amplifies the power of the sun by a factor of 10,000. Another use of parabolas is in flashlights and headlights. Flashlights and headlights will use a parabolic reflector behind the bulb. You put that bulb at the focus, and then the rays of light that are emitted by the bulb will bounce off of that parabolic reflector. So then all those beams of light come out parallel. We can see a lot better if we have a very focused parallel beam of light than if we didn't have that parabolic reflector and that light bulb just emitted a diffuse pattern of light. I'd much rather be driving my car at nighttime with those parabolic curved reflectors to help me out. This doesn't really use the property, but it is interesting to note that the cables of suspension bridges, like the Golden Gate Bridge that many of you might have seen before, form parabolas. So let's get into what we're going to actually do with parabolas. And before we get into that, we need to review a skill that's going to be super important for the next 3 sections of this chapter, completing the square, which you saw in your Algebra 1 days and in your Algebra 2 days. You should be very familiar with graphing parabolas when they're written in what your book calls standard form, but every other textbook calls vertex form. Okay? We know the number inside the parentheses is going to move our graph left and right. This number out here is going to move our graph up and down. And the number out in front of the parentheses is going to give us our stretches, shrinks, and reflections. And we can use completing the square to take an equation that's not in that form and transform it. So for our first example, we're going to look at y equals x squared plus 16x plus 63. And we're going to start by taking just the x terms and putting them inside of a set of parentheses. We're going to kick that plus 63 outside. It's not part of the parentheses party. It's just not cool enough. Okay? And you might recall this little formula that we use for completing the square. We're going to take our b value, the number in front of our linear term in front of the x term. We're going to divide it by 2, and then we're going to square it. So in this case, our b value is 16. 16 divided by 2 is 8, and 8 squared is 64. That is the number that we need to complete the square. Of course, when I add 64 inside of the parentheses, that would change the value of this equation. So I need to balance that out by subtracting 64 on the outside of the parentheses here. And now we're just going to do a little bit of factoring and simplifying to tidy this up. Okay? If I factor just the part that's in the parentheses here, the two numbers that multiply to give 64 and add to give 16 are 8 and 8. So I could write this as x plus 8 times x plus 8, or hey, that's the same as x plus 8 squared. And 63 minus 64, hey, that's -1. So now we have y equals x plus 8 quantity squared minus 1. Let me back up a second. Do note that this number inside of the parentheses is always going to be half the b value. Half of positive 16 is positive 8. That's what's going to go inside the parentheses. Okay? Now that it's in this form, I can look at it. I can tell where my vertex is. That plus 8 is going to move my graph left 8. My minus 1 is going to move my graph down 1. So my vertex is the point -8, -1. And I could put this on a graph. Okay? Go left 8, down 1, put my vertex. There's no stretch or shrink, so I know when I'm going over 1 from my vertex, my graph is going to go up 1 with that point on either side. You want more points. When you go over 2 from the vertex, your graph is going to go up 2 squared or 4. So 1, 2, 3, 4 spaces at this point right here. And same thing, 2 spaces on the other side of the vertex, up 4. There's our points. We can connect them to sketch our curve. Now that was a pretty friendly example. Let's take a look at a couple more. Next up, we have y equals -5x squared plus 15x minus 12. Again, we're going to start by putting those x terms inside of a set of parentheses. We're going to kick the -12 out. It's not part of the parentheses party today. Now notice this one's a little bit different. We have a coefficient in front of that x squared term. And so our next step is going to be to factor that out. So I'm going to factor out -5 from everything inside the parentheses. So now if I factor that out, -5 times x squared is -5x squared. -5 times -3x is that plus 15x. And now we're going to complete the square. Again, take half of your b value, half of the number in front of the x, and then square it. Now, your numbers are not always going to be pretty. Sometimes you're going to have to deal with fractions. Half of -3 is -3/2, or -3/2. And then if we square that, -3/2 squared, -3/2 times -3/2, 3 times 3 is 9, 2 times 2 is 4. So we're going to have to add 9/4 inside the parentheses. Now here's where many of you will be tempted to make a mistake, because we didn't just add 9/4. We added -5 times 9/4. Okay, well, -5 times 9/4 is -45/4. So to balance out a -45/4, I'm going to add 45/4 outside the parentheses. Now, if we simplify this, okay, you can either factor this or remember that what's going to be inside the parentheses is the same as your b value divided by 2, so -3/2. Out here, on the outside of the parentheses, you're going to have to get a common denominator if you don't have a calculator with a fraction button to help you. -12 is the same as -48 divided by 4. So -48/4 plus 45/4 gives us -3/4. Now this is in vertex form. We can look at it. We know our vertex is going right 3/2, down 3/4. We have a reflection over the x-axis and a vertical stretch of 5. So if we go right 3/2, down 3/4, there's our vertex. And then because of that -5 that's out in front of the parentheses, I know that when I go over one space from my vertex, I'm going to go down 5 spaces. See if I can get that pointer back to show us. Okay, so when we go over one space from our vertex, we're going down 1, 2, 3, 4, 5 spaces. Same thing on the other side, and we can sketch in our curve. Last part of this example, x squared plus 8x is equal to 2y minus 10. Notice that the x terms are already by themselves on one side of the equation. Okay? If we wanted, we could get it to look like the last two examples and get y by itself and then complete the square, but it's actually easier to complete the square with just the x terms isolated, and then we'll work to get y by itself at the very end. Okay? So, put our x terms inside the parentheses, complete the square. Half of our b value is 8 divided by 2, 4, and 4 squared is 16. So I'm going to add 16 inside the parentheses, and there's nothing in front to multiply it by. So to balance out that plus 16, then we're going to subtract 16 outside the parentheses. If we factor this, okay, half of 8 is 4, so we're going to end up with x plus 4 squared. Then our minus 16 equals the 2y minus 10. And now we want to get y by itself. So if we add 10 to both sides, negative 16 plus 10 gives us negative 6. And now we're going to divide by 2, or dividing by 2 is the same as multiplying by 1/2. So we're going to get 1/2 times the x plus 4 squared, and 1/2 of negative 6 is negative 3 equals y. So looking at this, hey, we've got a vertical shrink of 1/2. This graph is going to be shifted left 4 and down 3. So our vertex is negative 4, negative 3. Put our vertex on our graph. And then if we go over one space from our vertex, we should be going up half a space on either side. Put those points on our graph and we can sketch in our curve. The standard equation of a vertical parabola. So this chapter is going to look a little bit different. Okay, especially because we're focused on now not just the vertical, but the horizontal parabolas. So we have the quantity x minus h squared is equal to 4p times the quantity y minus k, where your vertex is the point h comma k. P is the distance from the vertex to the focus. So here's your vertex, here's your focus. P is that distance between those 2 points. If you want, you can write down these formulas for the axis, focus, and directrix, but honestly, as long as you know how to find your vertex and that you understand the distance, that P represents the distance from the vertex to the focus, you can figure the rest of those things out. Notice that when P is positive, your parabola will open upward, and when P is less than 0, when it's negative, your parabola is going to open downward. So let's use this to write the equation of a parabola in standard form, sketch a graph, and identify the key features. So if we start with an equation that's typically known as being in a vertex form, y equals 2 times the quantity x minus 3 squared plus 4. We want to get that into standard form, which means we need to get the square term by itself. I'm going to start by subtracting 4 on both sides, and then y minus 4 is equal to 2 times x minus 3 squared. Now we need to get rid of that 2 that's out in front. Pardon me. So we can either divide by 2, or that's the same as multiplying by 1/2. So now we have 1/2 times the quantity y minus 4 is equal to the quantity x minus 3 squared. This is standard form. We can look at this and know that the x-coordinate of our vertex was moved right 3. The y-coordinate of our vertex was moved up 4. So our vertex is the point 3, 4. To identify the other key features, we need to find the value of p. And to do that, we use the number that's out in front of our y set of parentheses. Okay, we call this as our standard form equation. So this 1/2 is equal to 4p. So if you divide both sides by 4 to get p by itself, 1/2 divided by 4 is 1/8. So p is 1/8. The distance from the vertex to the focus is 1/8. So our focus is going to be 1/8 of a space above our vertex, which means, which we can see on our graph here, a little bit hard to see because it is such a small distance. But that puts our focus at the point 3, 4 and 1/8. If you want to write these as improper fractions, 33/8, that's also fine. Our axis of symmetry, that line down the middle, is at x equals 3. In a vertical parabola, it's always going to match the x-coordinate of your vertex. Our directrix is this line underneath. It's going to be the same distance in the opposite direction as the focus. So since our focus was 1/8 of a space above our vertex, our directrix is 1/8 of a space below that vertex. So 1/8 of a space below 4 is going to be 3 7/8. So this line is y equals 3 7/8, or that would be y equals 31/8 if you wanted to write that as an improper fraction. Let's try another one. Slight difference. If that number out in front is negative, same process for finding it in standard form, right? We need to isolate the square term, subtract our 4, divide by -2, or multiply by -1/2. And there's our standard form. Our vertex is the same at 3, 4. If we find our p-value, this time -1/2 is equal to 4p, which means p is equal to -1/8. So when we have that negative p-value, we know our parabola is going to open down. So our focus is 1/8 of a space below our vertex. 1/8 of a space below 4 is 3 7/8. So our focus is at 3, 3 7/8. Our axis of symmetry is still the same, x equals 3. Our directrix now is going to be above the vertex. So 1/8 of a space above 4 is going to be at 4 1/8. So our directrix is the line y equals 4 1/8. Please note that when you are identifying the vertex and focus, you need to write the coordinates of the points. When you are identifying the axis and directrix, those are lines. You have to write them as equations of lines. If all you write for the axis is just the number 3, you will not receive credit. So watch out for that. All right. Next up, horizontal parabolas. The standard form of the equation for a horizontal parabola is the quantity y minus k squared is equal to 4p times the quantity x minus h. If you compare this to our vertical parabola, notice that the square is now on the y set of parentheses, and the 4p is in front of the x set of parentheses. Our vertex still has the coordinates h, k. P is still the distance from the vertex to the focus. If you want to write down the little formulas for axis, focus, and directrix, you can. In a horizontal parabola, If your p-value is positive, your parabola will open to the right. And if your p-value is negative, your parabola will open to the left. So let's identify the key features for the equation. The quantity y minus 5 squared is equal to negative 8 times the quantity x plus 3. Since the y term is being squared, we know this is a horizontal parabola. And since the number in front of the x set of parentheses is negative, we know this parabola opens to the left. You might even find it helpful to sketch a little picture. It doesn't even have to be accurate. Just having a parabola that's facing to the left so that you can kind of picture where things are in relation to each other can be very helpful. Okay? Let's start with our vertex. The plus 3 means our x coordinate's going to go left 3. The minus 5 means our y coordinate's going up 5. I guess I did it in a different order in the PowerPoint. That's okay. Let's find our p-value. We know the number out in front is negative 8. So negative 8 equals 4p, which means p equals negative 2. All right, there's our vertex that I was talking about a moment ago at negative 3, 5. So our focus is going to be 2 spaces to the left of our vertex, which would be the point negative 5, 5. Our axis of symmetry, that line down the middle, okay, it's crossing through the y-axis, so I know it's starting with y equals, and our y coordinate here is 5, so our axis of symmetry is going to be y equals 5. Our directrix, okay, our p-value is negative 2, so our directrix is going to be 2 spaces to the right of our vertex. 2 spaces to the right of negative 3 is going to be negative 1. Our directrix passes through the x-axis, so that equation is going to start with x equals, so x equals negative 1 for our directrix. Example 4, we're going to find the standard equation of a parabola with a vertex at the point 3, 2 and a focus at 8, 2. Again, when you're given information like this, it can be very helpful to sketch the parabola before you write the equation. And again, it doesn't have to be a super accurate sketch, just having the places, the points, and labeling them so that you can figure out whether your parabola is horizontal or vertical, whether it's opening left or right, is very critical to being able to write the correct equation. Since our focus is to the right of our vertex, we know this is a horizontal parabola, and it has a positive p-value. In fact, that p-value is 5, right? If our vertex is at 3, 2, our focus is at 8, 2, there's 5 spaces in between those 2 points. Now, if you recall, there's our standard form, y minus k squared equals 4p times x minus h. A very common mistake on these problems is to use the coordinates of the focus instead of the vertex. So make sure that you're using the vertex because that's where our h and our k come from, okay? Also, make sure you're putting the coordinates in the correct place, right? Put the x coordinate of the vertex in the x set of parentheses, put the y coordinate of the vertex in the y set of parentheses. Watch out for when there's negative signs, right? Because this is x minus h. If your h value was a negative 3, when you subtract a negative, that would turn into a positive, okay? So we're going to put our 2 in for k, we're going to put the 3 in for the h, we're going to put 5 in for the p. 4 times 5 gives us 20. So we end up with y minus 2 squared equals 20 times the quantity x minus 3 for our equation. And we have one more example, I believe. Example 5, we're going to write the equation in standard form. Fun equation for you, or a more interesting equation for you than the ones that we saw earlier. So this time we have x squared plus 2x minus 3y plus 13 is equal to 0. Again, we're going to need to complete the square. So get those x terms inside of a set of parentheses. Now I should caution you, If it was a horizontal parabola, the y term was squared, then you would need to get the y terms in a set of parentheses and kick everything else outside. Okay, so x squared plus 2x inside a set of parentheses, kick everything else outside the parentheses, minus 3y plus 13, and we still have it equal to 0. Okay, to complete our square, looking at our b value 2, half of 2 is 1, and 1 squared is still 1. Hey, that's kind of nice. So we're going to add 1 inside the parentheses and balance it out by subtracting 1 on the outside. Now, if we factor this, half of 2 is 1, so we end up with x plus 1 squared, and then minus 3y. 13 minus 1 gives us a positive 12, still equals 0. Now we want to get our squared term by itself. So to get rid of a minus 3y, we're going to add 3y. To get rid of the plus 12, we're going to subtract 12. So now we have the quantity x plus 1 squared equals positive 3y minus 12. And to get it all the way into the standard equation form, we need to factor this left side. Even if it doesn't go in nicely, you want to factor it so that the y is by itself on the inside of the parentheses as the first term. In this case, it does go in nicely. You can factor out that 3 very easily. 3 times y is 3y, 3 times negative 4 is negative 12. So our new equation, our final equation, is the quantity x plus 1 squared is equal to 3 times the quantity y minus 4. Now that's in standard form. We can look at this, we can tell our vertex, we can see that our 3 is going to equal 4p, so we could solve to find p and then identify our other key features and sketch a graph if we had been asked to do so. Your assignment you can see here is on page 704, which you can do in the book and then email me a picture, or you can do it on WebAssign. After you finish the assignment, you do have a comprehension check and then a Google check-in form. Please make sure that you do all 3 of these things. Many of you are going to be receiving an email from me letting you know that you did not complete everything from week 1. So you might have some extra work to do this week to get caught up. Please reach out if you need help. I am checking email regularly, or you can chat with me during office hours on Monday, Tuesday, Wednesday, or Thursday. Thank you and good luck.